This is our last notes on rotation. We're talking about angular momentum today. We've gone through rotational kinematics. We've talked about torque, which is kind of like forces, but it's at a force at a distance. It's what causes an object to rotate. We've talked about static equilibrium, when it's not in static equilibrium and things are angularly accelerating. Talked about energy and work. And lastly, we're here to talk about angular momentum. Angular momentum, as you'll see right here, uses the letter L. I know, I don't get it. We use L for length. I have no idea why L is used for angular momentum. And the units are going to be kilogram meters squared per second. The rest of these variables you should recognize. Capital I, the moment of inertia. The scripty W, that's omega, angular velocity. R is the distance from the axis of rotation. M is the object's mass. V is tangential velocity. The scripty letter T there, that's tau, applied torque, and then change in T just means time elapsed, or how much time has gone by. We have two equations for angular momentum. The first one here, angular momentum is the moment of inertia times angular velocity. Kind of like regular momentum was mass times velocity, this is the moment of inertia times angular velocity. We can also calculate angular momentum by finding the distance from the axis of rotation and multiplying it by the mass and the velocity. So if you find the object's tangential momentum, right, momentum in the x or y direction, and you multiply that by the distance from the axis of rotation, that's the other way to find angular momentum. Just like our old unit in momentum where you could find the change in momentum, that was force times time, the change in angular momentum is torque times time. Okay, these are very similar to momentum in our previous unit, but now we have to deal with a rotational aspect. So two equations for angular momentum and an equation for change in angular momentum. Let's go into our first question here. It says determine the angular momentum for a sphere of mass 3 kilograms and radius 1 meter, and it's rotating at 20 radians per second. Big thing to note here is it's a sphere. We've got the mass, the radius, and the velocity. So I'm going to look at my two equations here and decide which one to use. Because it gives me the angular velocity of radians per second, I'm going to look at this first equation and try that one. The moment of inertia for a sphere is 2/5 mr squared, and then we've got multiplied by omega there, so this is 2/5, the mass is 3, the radius is 1, and the angular velocity is 20. And if we multiply that all out, we get 24 kilogram meters squared per second. I have to try to memorize those units there. But that's our final answer, 24 kilogram meters squared per second. How did I know to use this equation? Well, I was given angular velocity, I was given mass in the radius. If you use the second equation here, you'd have to convert this 20 radians per second into a tangential velocity, and it still would have worked. I should have got the same answer. Keep this quick, moving on to the next problem. 20 kilogram child riding 4 meters from the axis of rotation on a merry-go-round. The merry-go-round completes 10 rotations in 4 seconds. Determine the angular momentum for the child. Got a couple different options here. Remember, we have these two equations. We have this one and this one. I'm going to try to use this first one again and see if this works. Angular momentum equals the moment of inertia times angular velocity. We don't quite know either of these, but I'm thinking from the information given to us we can find them. The moment of inertia for this child, he's just rotating about this axis of rotation, so it's going to be mr squared. Mass is 20, the distance there is 4 meters, and we're squaring that. So the moment of inertia for this child is 320 kilogram meters squared. So that gives us the moment of inertia. To find angular velocity, it says that it does 10 rotations in 40 seconds. Well, angular velocity you can find by figuring out the angular displacement and dividing it by time. Angular displacement has to be in radians, so this is going to be 10 revolutions, and there's 2 pi radians in each revolution, and the total time there takes 40 seconds. So that's going to end up being about 1.57 radians per second. So let's plug both of these numbers back in over here. We get the angular momentum is 320 times 1.57. We get an angular momentum of 502.4 kilogram meters squared per second. If you decided to use our other equation, the second equation here, that would have worked as well. You would have had to converted this 10 rotations in 40 seconds into a tangential velocity. Totally possible. You guys could have done that. And if you wanted to, you could solve it that way, and you should get the same answer as me. Okay. Move on to our last simple example. 71. It says there's a torque of 20 Newton meters, and it's applied to a disk that's rotating for 30 seconds. Determine the change in angular momentum. So change in angular momentum is this. Scroll up here. There's the equation we're using. Change in angular momentum is equal to the torque times the change in time. So 20 times 30, and we get 600 kilogram meters squared per second. Okay, pretty easy for that one. Down below, it says that the conservation of angular momentum can be solved in several ways. Explain when to use each of the following versions. And this is really the big question in physics, right? You claim to understand physics, but you never know which equation to use, to which I would respond, well, then you really don't know what you're talking about. That just means you can do the algebra if you're given the equation, but choosing the equations to use, that's part of the physics, understanding the concepts and when each is appropriate. Now, momentum is conserved here, conservation of angular momentum, just like the last unit, right? The last unit we'd say the initial momentum is equal to the final momentum, but we only had the same equations for both of these, right? That was our only equation for the last unit. Now we have two of these. We have the moment of inertia times angular velocity. We also have this RMV. All of these are true, and they're each advantageous to use at different times. It totally depends on what information you're given. If you're given the initial angular velocity and the initial moment of inertia, or you can solve for those, well, then you're going to use one of these two equations. Instead, if you're given the final tangential velocity, the mass and the radius, then you're going to use this equation or this equation, okay? It totally depends on which one you're going to use. So let's do a couple of examples on this next page, and we'll decide which one is advantageous to use in each of these cases. 73, it says two 5-kilogram masses are located at the end of a 2-meter long bar. So we've got a mass here of 5 kilograms, a mass here of 5 kilograms. This bar is 2 meters, and it's spinning around, okay, at 4 radians per second. It says the mass of the bar is negligible. So this is spinning around this way. The length of the bar then decreases to a distance of 1 meter. So as it's spinning around, these masses move in, 5 here, and it becomes a distance of 1 meter. And we want to figure out what is the new speed of this apparatus. And you've seen this when ice skaters are going, right? An ice skater will spin like this with their arms out, and then they bring their arms in, and they speed up. So let's figure this out. Momentum's conserved, so we have initial angular momentum equals final angular momentum. Which one am I going to use here? Well, these are masses at the end of these rods. The rod doesn't have any mass, so it's pretty easy to find the moment of inertia for this. We're given the angular velocity, so I'm just going to use this simple one. I'm going to say the initial momentum equals the final angular momentum. The initial momentum here, that's going to be mr squared, right? So we're going to have this mass, and that's 1 meter away, so that's squared, plus this mass, which is 1 meter away. The angular velocity to start is 4. The final angular velocity, if this is our axis of rotation here, each of these are a half a meter away. So this 5-kilogram mass is a half a meter away. This 5-kilogram mass is a half a meter away. And we're finding this final angular velocity. Work all this out, you get 40 equals 2.5 times the angular velocity. You get an angular velocity of 16 radians per second. Now, if this had asked me to solve for the tangential speed, I could have solved for angular velocity and converted it, or I could have used a different final angular momentum. But the big idea is that angular momentum is conserved. Choose your equations, make sure they're ones that you can solve for everything except for what you're looking for, and solve for that final angular velocity in this case. Let's move on to the next problem. It says a 1,000-kilogram satellite is in an elliptical orbit about Earth, and its closest approach to Earth is a distance of 1.5 times 10 to the 7th meters away from the center of the Earth. At this distance, the satellite has a speed of 5,000 meters per second. 6 months later, the satellite is 2 times 10 to the 7th meters away. What is the satellite's speed there? So again, we're going to be using conservation of angular momentum. This time we're given meters per second for speed. We're given the distance away. We're given the mass. We could go about this using moment of inertia and angular velocity, but instead I'm going to use the other ones. I'm going to use the initial radius times mass times the initial velocity equals the final radius times the mass times the final velocity. You could have used the other ones. You would have had to convert some things and figure that out, but this is the simplest one. Your biggest problem is going to be choosing which one to use. Figure out what variables you know. Maybe write down an equation. Try it one way, and if you can't figure out one of those variables, try the other equation. Okay? So let's plug all this in. That first radius, 1.5 times 10 to the 7th meters. The mass is 1,000. Oops. The initial velocity for this, it says, was 5,000 meters per second. The final radius here is 2 times 10 to the 7th meters. The mass is still 1,000. I guess I could have canceled those out if I really wanted to. And we're solving for this final velocity. Multiply all these out, divide by each of these, and you get a final velocity of 3,750 meters per second. Okay, big idea. Angular momentum is conserved. Choose which equation you want to use for initial angular momentum. Choose which one you want to use for final momentum. Plug in your variables and solve for the unknown. Very last problem is a catapult. In this problem, we have a catapult that's got a lever arm like this, and then on the end of this lever arm is a box, and here's our axis of rotation. It says a catapult is used to launch a 10-kilogram projectile, so there is a 10-kilogram projectile in here. The arm of the catapult has a mass of 30 kilograms and a length of 5 meters. At the instant that the arm releases the projectile, the system has a rotational speed of 2 radians per second. So at some point this turns and this projectile is then released. And at this speed, when it's going, it's rotating at 2 radians per second. Determine the tangential speed of the projectile as it leaves the launch arm of the catapult. So we want to figure out what is this speed of this catapult. So let's go through this here. Right before it releases, this has a speed, an angular speed of 2 radians per second. And we want to figure out what is the speed after it's left. So we're going to use conservation of momentum again, or conservation of angular momentum. And this one's a little different. We have to play around with it, which I did in my notes for a little while. And I'm actually going to use the initial moment of inertia times the initial velocity, angular velocity. And for the final angular momentum, I'm going to do radius times the mass times the velocity. Okay? This part here is for the catapult, everything all together. And then as soon as this is released and this arm stops, this part over here, the only thing that's moving now is the projectile. So what is this moment of inertia for the initial object? Well, we have two things. We have this bar here, so we have to have the moment of inertia for the bar. We also have the mass on the end of that bar. The moment of inertia for the rod rotating about its end, that's 1/3 mass of the rod times its length squared, and then we have the projectile here. Its moment of inertia is just going to be the mass of that projectile times its distance squared. Then we've got the initial velocity, and that's equal to the final angular momentum, RMV, where this is just the mass of the projectile. So let's go in, we'll plug in these numbers, 1/3 times 30 times 5 squared, plus 10 times 5 squared. The initial angular velocity was 2 radians per second. Radius is 5. The mass of just the projectile is 10. And we have the final velocity here. So this ends up being 500 times 2 equals 50 V. And so the velocity of that projectile is going to be 20 meters per second. So there's your quick lesson on everything angular momentum and conservation of angular momentum. And I look forward to having you in class next time to work on some of those problems.